Hi, welcome to our next lesson on gas pressure. So let's talk about what causes gas pressure. It turns out that when the gas particles that are constantly moving, we learned about that in our lesson on gas properties, we learned that the kinetic molecular theory tells us that gas particles are constantly moving in rapid random motion. And because of that, those particles are going to eventually crash into the walls of their container. When they crash into the walls of their container, it puts a force on the container. If we add up all those forces, that is what gas pressure is. So gas pressure is the sum of all the forces of the gas particles hitting the walls of their container. So anything that changes the number of collisions, so I could have more or fewer collisions, or anything that affects the strength of those collisions, so if they're stronger or if they're weaker, anything that would affect these two things will affect the pressure. So once again, just really quickly, what causes gas pressure? Gas pressure is caused by collisions. All right? And anything that can affect those collisions can affect the gas pressure. Well, let's look at the first one at volume. So here's a picture of a four-stroke engine. And in a four-stroke engine, we have a piston. So here's the piston. And this is in four separate stages here. And what happens is the piston moves up and down inside the cylinder, giving the gas more or less room to be in. And so it's changing the volume, right? So in this first case, we have a decent sized volume for the gas to be in. And so the gas is relatively spread out, low pressure. These gas particles are not going to run into the walls all that often. But in the second picture here, we have reduced the volume. The volume has gotten smaller. And so now the gas particles are much closer together. And because they're much closer together, they're going to run into the walls more often. And so this is an area of increased pressure. So this is high pressure. And over here where there was more space, this is lower pressure. So as you can see, volume and pressure are related to each other. And we would say that the pressure is proportional to the inverse of the volume. So we would say, and what this means here is that if pressure and volume are inversely proportional, it means that if the volume were to go up, like in this first case, the volume goes up, then the pressure goes down. See how they're opposite from one another? That's what we mean by inverse. Also, if the volume gets smaller, so if the volume goes down, then the pressure gets bigger. So they are inversely proportional to each other. Now, how is it that volume affects pressure? Well, by decreasing the volume, I'm affecting the number of collisions. Not so much the strength of those collisions, but I'm definitely affecting how many times the particles collide with the wall, and that's why volume affects gas pressure. Another thing that can affect gas pressure is temperature. And if you remember, we learned that temperature, we learned this in our thermodynamics unit, that temperature is actually a measure of the speed of the particles. So the faster they move, the higher the temperature. The slower they move, the lower the temperature. Well, if you think about this, the faster they move, that's going to increase how hard they hit the walls of their container. A good example of temperature affecting gas pressure is a hot air balloon. Let me grab something a little bit brighter for you to see. Let's try this. The gas particles, as they're getting heated up, are moving faster and faster and faster, and it turns out that they're also very far apart from each other. But as they're getting heated up and they're hitting the walls of their container, they hit faster. And so this is an area of high pressure inside because they're hitting the walls of their container really fast. But the air outside the hot air balloon is low pressure because these gas particles are moving much slower and they are hitting the walls of the container much less often. Well, because there is high pressure inside and low pressure outside, the high pressure will rise up through the low pressure. So here we learn that pressure is also proportional. It's related to temperature, which we're going to use capital T for temperature. But in this case, it's different than the volume, because in this case, as the temperature gets bigger, so does the pressure. So we say that pressure and temperature are proportional to one another. What this means is that as the temperature goes up, the pressure goes up too. Or as the temperature comes down, the pressure will also come down. This is a proportional relationship. So how is it that temperature affects pressure? Well, because the particles are moving faster when they're hotter, it definitely affects the strength of the collisions. But also, if they speed up and they're zipping around faster and faster and faster, it's also, so this is and, it's also going to affect the number of collisions. So temperature affects pressure not only by increasing the strength of the collisions, but also by increasing the number of collisions. So what's something else that might affect gas pressure? How could we make more or less collisions or stronger or weaker collisions? Well, another thing that could affect it is concentration. And by concentration, I mean how many particles there are in a given area. Or another way to think about this would be the density of the particles. Well, the more crowded the particles are, the more dense they are, the more likely they're going to run into the walls of the container. This is very much the same concept as decreasing the volume. When you decrease the volume, you increase the density or the concentration of the particles in that space. So an example of increasing the concentration might be filling up a tire with air. So maybe this is a flat tire, and because it's a flat tire, there aren't very many gas particles in it, and so they're very far, they're not crowded, it's very low density, and so it's not very concentrated. And so this would have a low pressure. But as we pump air in, so here's a whole bunch of gas particles, and we're moving these all into the tire. So after we've added the air, now the gas particles are very close and tight to one another. They're very crowded. Because they're crowded, they're going to run into the walls of that tire more often. And because of that, now the pressure inside is high. And so we're going to read a higher pressure reading. So how is it that concentration affects pressure? Well, I don't know that concentration so much affects the strength of the collision, but it certainly increases the number of collisions. And so by adding more particles, we have more collisions, and that's why the gas pressure goes up. So once again, pressure is proportional to the concentration. Now, a way that we talk about concentration is we use N. N actually stands for the number of moles. But in this case, we're going to talk about concentration. And it turns out that it is also proportional, because as the concentration or as the number of particles goes up, so does the pressure, and vice versa. So a lot of people have questions about air pressure. If pressure is caused by air particles hitting the walls of their container, but air on Earth isn't really in a container, so what causes air pressure? Well, air pressure is actually the sum of the forces on us, you and me, or on the surface of the Earth. Because you realize that as we stand in the air, the gas particles out here are zipping around and they're putting pressure on us, right? So here's some more gas particles, they're putting pressure on us. Or if it was the surface of the Earth over here, they are also putting pressure on the surface of the Earth. Well, it turns out that gravity can affect the density of air, because the closer the air is to the surface of the earth, the stronger the pull of gravity is, and so the air particles are more concentrated. And because they're more concentrated, they run into things more often, and that's why at sea level the air pressure is greater than it is if you go to the top of the mountain. At the top of a mountain, the air pressure is less because the particles are further spread apart because gravity isn't pulling on them as hard. Another thing that can affect air pressure is temperature. So this is how our weather patterns emerge. If the air particles get warm, then the air spreads out, it becomes less concentrated, and so air pressure goes down. However, those particles speed up, and so that can cause air pressure to go up. So air pressure is affected by a combination of gravity and temperature. So you might be wondering what we measure air pressure with. Air pressure is measured with a device called a barometer. The original barometer looked like the picture here on the left, where we have a column of mercury, and then there's a dish that has liquid mercury in it. And so the air pressure, the air outside, is pushing on this pool of mercury. And if this air pressure is greater than the air pressure inside the column, then the column will move up. And so if the air pressure outside is high, you get more millimeters of mercury in your column. If, however, the air pressure is low, maybe we have a day of a storm coming up, and so the air pressure outside is low and the air pressure inside is greater, then the mercury would move out and the column of mercury would move down, and so you would have fewer millimeters of mercury on a stormy day. Nowadays, we don't use barometers that look like this. We have analog or digital barometers that measure things in units like millimeters of mercury or pascals or kilopascals. And then barometers also come in some very decorative designs, and these are sort of interesting. Both of these designs work on the same principle. They have an opening that's exposed to the air outside, and then inside they have a container that has some pressure inside. So here, if the outside air pressure is greater than the pressure inside, then this column of fluid will move down the arm. But if the air pressure outside is less than the pressure inside, maybe the pressure inside is greater, then this column of water would move up. And so these are just different ways to measure the air pressure outside. The last thing that you need in order to deal with air pressure or gas pressure is you need to understand that we have different units that we measure air pressure in. The most common that we use in chemistry are the atmosphere, millimeters of mercury, this comes from that original barometer design, a unit called a kilopascal, and then also a unit called a torr. You need to know this equality statement in order to do conversions between different pressure units. Also, there are some other, because we live here in America, there are some other pressure units that you might hear. We don't use them in science so much, but you might hear them in your everyday life, and so I just wanted to present those to you as well. So here, I've compared them all to the atmosphere, so you can get an idea of how they relate. This is a millibar, and you'll notice that a millibar is related to a kilopascal. It turns out that 1 bar is 100,000 pascals, or 100 kilopascals. So they're just off by a decimal. I mean, it's a power of 10 that they're different from. Also, we have this unit PSI, which is pounds per square inch. And then in America, sometimes you will also see barometers that read in inches of mercury. We will not, however, be using bars or PSI or inches of mercury in this science class. You just need to know the 4 units up top and how to convert. Hope that helps with your worksheet.